Engineering Mechanistatics Lecture 12. In this lecture, we are going to learn about the last part of equivalent system, which is reduction of a simple distributed loading. This is the objective. Student will be able to determine an equivalence force for a distributed load. This is one of the example of distributed load. A distributed load on the beam exists due to the weight of the wood. Is it possible to reduce this force system to a single force that will have the same external effects? If yes, how? Okay, before this, we have a system like this. Say we have a beam here, and then we apply a couple of force on the beam. So let's say this is F1, F2 and F3. So we change the system into one equivalent force, Fr. Okay, so where Fr is equals to F1 plus F2 plus F3. This is where the force is in the form of point. So this is one point, this second point, and this is third point. What if the force have a distributed section like this? Okay, so this is all the force. Let's say this is 10 kilogram. Okay, so this is what we call a distributed force. Okay, there are many points of force here. Okay, so like this. And then how we want to represent this system into one single resultant force. Or maybe the distributed force has the form like this, or like this. Okay, so how we want to find the resultant force if the force exerted is distributed force like this and this one? Okay, so what we need to do first is map the distributed load on the axis. Let's say we have a distributed force like this. So we put this onto the an axis of x and y. Okay, so same goes to if we have a distributed load like this one. So we have an axis like that. Okay, so this we can represent like this. Okay, so this is actually show a curve on a graph. Okay, so like this one, like this one. Okay, so this is a constant graph, and this one is a linear graph. Okay, let's say we take this one. Okay, a linear graph, x and y. So this one, let's say we have a data like this, xy. So if x1, y is 2. If x2, y is 4. Okay, so we can plot here. this is 1, 2, 3, and then the y is 2, 4, and 6. Okay, so which means that y over x is equal to 2. Sorry, is equal to 2. Okay, so this means that y equal to 2x. So this is the function of the graph here. If let's say any form of graph like the exponential graph or any other form of graph, we don't know the function here. So we don't know y over x is equal to what. So we can simply denote this as w in a function of x. Okay. So any form of the curve, we represent it as w in a function of x, which means that this is equal to y over x. So we can use this equation to represent our distributed force. Okay, if let's say our distributed force is like this, okay, so the line of curve here is w. We represent it as w in a function of x. So this is your f and this is your distance, and the force here is distributed along the distance x here. So your equation become like this: f over x is equal to wx. Okay, if let's say we generalize this equation, let's say we take from this point to this point, so from x1 to x2, from f0 to f y somewhere here. So if we can generalize this, let's say we take this portion, so x2, we must take the difference between x1 and x2, so x2 minus x1, the upper is fy minus f0. Okay, so the difference here, this one is the difference of force, and the lower here is difference of x, okay. So difference of force means that we can write it as df, differential of force, okay, and difference of x we can write this as dx, means that differential of x. Okay, so we write this into the equation here, so it becomes df over dx equal to wx. So to get the resultant force of Fr means that you want to find the total force, or the total amount of force, the resultant force. Okay, so means that you want to know the total amount of this force. Okay, so in this region, because the force is distributed along the region here, so you want to find the resultant force, the total amount of force. So you need to actually integrate the differential equation here. So this is, if you still remember, this is the subject of additional math or engineering calculus. So when you do the integration of differential df equal to differential x dx, so if you differentiate differential of f here, so you will get, if you integrate the differential f here, so you will get the total amount of this region, or simply we can say that this is the area of this region, so this is equal to area. Okay, one more thing, please remember that the function of wx here is actually equal to force over x, so this, the unit of wx here is equals to, the unit is Newton over meter. Okay, so when you integrate this differential of f, so you will get the resultant force, which means that integration of df is equal to f resultant. So that's how you get the force resultant of distributed force here. So if we can draw the diagram, it is looks like this. Okay, so let's say this is a df, and then okay, this is the f. Okay, so if let's say we want to find the moment resultants, so how we gonna do it? So this is like we have a, let's say we have a resultant force here, Fr. So we need to find the, call it as x bar, where m resultant is equal to x bar multiply with f resultant. Okay, so this is equals to x, we take for the f is x here, x, f resultants, we take this equation, so multiply with integration of df. Okay, this is equal to integration of x w x dx. Okay, means that if you want to find the x bar, so this is equal to x bar is equal to m resultant divided with f resultant. So replace these two value with the equation here and here. So f resultant is equal to this one, and then m resultant is equal to this one. So this is equals to x wx dx, and then integration of wx dx. Okay, so you get this one. So for conclusion, distributed loading are defined by using a loading w equals to wx that indicates the intensity of the loading along the length of the member. This intensity is measured in Newton over meter, which means that we just discussed previously F over X. Okay, so the external effect caused by a coplanar distributed load acting on a body can be represented by a single resultant force. So we can change the distributed load into the single resultant force by doing the integration method. Okay, the resultant force is equivalent to the area under the distributed loading diagram and has a line of action that passes through the centroid or geometric center of this area. Okay, that's it.